Hey guys, this is Vince Indris. I am the creator of Mr. Indris' Science Brainery, and this is MS-PS1-1 For Teachers. So your state has adopted the next generation science standard, or at least some type of the next generation science standards, and this has led to a lot of anxiety with some teachers. Some teachers think this is the greatest thing in the world. It's going to save humanity and eradicate all evil. Some teachers think that this is the evil that needs to be eradicated. So I hope that I'm exaggerating, but if you fall in one of those two camps or you are somewhere in the middle, I hope this video will address some of your concerns at least. I generally hear about three things from teachers. These are the big ones that come up, and that is, number one, what the heck am I supposed to teach? So I'll put some of that in this video, and the second one is exactly what do we do with content? Is it, so content versus students doing things, so knowing things versus doing things. And the third question that I always hear is, how is this going to be assessed? Because like it or not, at the end of the day, your state is probably going to give a test, and you probably will be evaluated on that test. And so it's good to know exactly what are we supposed to do. Okay, we have them doing something, but then how are you going to see if they actually retained any knowledge, and is there any knowledge they're supposed to retain? Or so what exactly is at work there? So anyway, there are three sections to this video, and that's number one is, what the heck am I supposed to teach? And number two is, how important is this content? And number three is, how is this going to be assessed? So if you have gone on YouTube and looked, I have a video entitled MS-PS1-1 Models of Atoms and Molecules, and that's for teachers who might need a rehatch of those things, or students who've never heard those things. But in that video I'm going to use, I have some essential questions that I use, and I walk through those essential questions. And I'm about to show you how I came up with those essential questions. So this is section one, what the heck am I supposed to teach? This is going to get kind of technical, and which means for some of you very boring, but for some of you, well, like me, it means, well, very exciting. We're actually going to look at the performance expectation and see what happens. So let's, if this is the boring kind to you, feel free to just skip on by to the second question. But for those of you who are anxiously awaiting, let's jump into it. This is the performance expectation. That's what we call this thing right here, develop models to describe the atomic composition of simple molecules and extended structures. Now this right here is a clarification statement to try to help you understand this. And then there's this assessment boundary, and that is what the assessment is limited to. Now, when we talk about 3D learning or 3D teaching, all this three-dimensional stuff, these are the three dimensions right here that they're talking about. Science and engineering practice. This is what the kids should be doing. Now, it's not all the kids should be doing. There's a lot of these things, and they have a lot of different ways to teach science. But, you know, whoever wrote the framework for this, they decided in their grand wisdom that in teaching this particular disciplinary core idea about atomic composition, they should be doing this scientific engineering practice. And then we always want to have these things in mind, cross-cutting concepts. Those are things that flow throughout all of science, all of life sciences and earth sciences and physical sciences, and everything you talk about really has something to do with these cross-cutting concepts. And again, this one is in particular supposed to be looked at while teaching this certain standard. It doesn't mean it's the only thing, but it certainly means that it is it's easier to teach that. Or maybe we should say that this performance expectation facilitates the teaching of this certain cross-cutting concept. And then, of course, we have the disciplinary core idea, and this is the one teachers tend to like a whole lot because this is the content. So let's go through them and see what we have. First, let's just look at the performance expectation. Develop models to describe the atomic composition of simple molecules and extended structures. When we do that, we want to look at our science and engineering practice, developing and using models. Modeling in 6 through 8 builds on K through 5 and progresses to developing, using, and revising models to describe, test, and predict more abstract phenomena and design systems. Develop a model to predict and or describe phenomenon. So we definitely want to develop models. That's what this is all about, developing some sort of model. And then once we do that, we're looking at this cross-cutting concept, and that's scale and proportion and quantity. So time, space, and energy phenomena can be observed as various scales using models again. So we're making sure we use models to teach them that there are small things that we can't see, so we have to make it bigger so we can see it. And in that, again, we're looking at the word models. Well, let's look at our disciplinary core idea. PS1A, structures and properties of matter. Substances are made from different types of atoms, which combine with one another in various ways. Atoms form molecules that range in size from 2 to 2,000 of atoms. So the different types of atoms is the big deal here. And what I'm going to discuss in the video will be elements, is what we call those, different types of atoms. And they're combined with one another in various ways. So we want to talk about those bonding together. Some atoms do bond, and some don't. And those that do bond form molecules. So the atoms that don't bond together we call inert atoms, or noble gases, or inert gases, and they don't bond, and we do have molecules that do bond. Solids may be formed from molecules, or there may be extended structures with repeating subunits, and that's like crystals, they say. So we want to figure out, well, what is an extended structure? What does that mean? What is a repeating subunit? And we have this whole crystal thing, so we want to make sure we touch on crystals. So let's see how that goes into our standard. Develop models. I underline that in blue because that is from the science and engineering practice. Develop models. To describe the atomic composition, so that describing comes from our cross-cutting concept, and that's why I put it in green, that we use these models to describe things that are too large or too small. The atomic composition of simple molecules, and I underline that in orange because that comes from the disciplinary core idea, talking about these simple molecules, and the extended structures. And again, that comes from our disciplinary core idea. Well, luckily, the writers of the NGSS gave us this clarification statement, and that's going to hopefully help us out in this performance expectation. It says, clarification statement. Emphasis is on developing models of molecules that vary in complexity. So we want to show things that are very, very simple, and we want to show things that are very, very complex. Examples of simple molecules could include ammonia and methanol. So now, those are examples. You don't have to, but I certainly want to make sure that I give them an example of ammonia and methanol, since those are two that were actually given to me from the clarification statement. Examples of extended structures could include sodium chloride or diamonds. And again, I'm going to introduce the kids to sodium chloride, and I'm also going to introduce them to diamonds so they can see what the extended structures look like. Example of molecular level models could include drawings, 3D ball and stick structures, or computer representations showing different molecules with different types of atoms. And so I want to point out, though, the drawings, that we seldom think of drawings as a model, but it is a model. You are modeling those things when you're drawing. So just simply drawing this stuff on the board or in their book is a model that they're doing. Of course, you will also want to get out, if you have the toothpicks and the styrofoam balls to make a model, you can do that too. And of course, every kid wants to get on their computer and look for, if they can design it, they have a program for it, they can design a computer representation. But drawing is also models. I wanted to point that out. We also have this assessment boundary. So for those of you interested in assessments and how this is going to be assessed, if your state has adopted this assessment boundary, then that means that the assessment will not include valence electrons and bonding energy, discussing the ionic nature of subunits of complex structures, or a complete description of all individual atoms in a complex molecule or extended structure is not required. Now that's an awful lot there, and in some ways I'm glad they're not assessing that because I don't understand everything I just read. But I do know that it said valence electrons. That's if you ever drew the little Bohr atom, that means the atom that has the electrons going around it and the shells have to be full. That's not going to be assessed. You don't need to know what atoms are going to bond with what atoms. You don't need it. We're not going to need to teach compound versus ionic bonding. So, and we'll see that more when we get to MS-PS1-1 on chemical structure and chemical bonding. But those are things that are not going to be included. Valence, electrons, and bonding energy. Nor are we going to have to know a complete description of all the individual atoms. And that would be a lot anyway. So kids that are wanting to memorize the periodic table, or teachers who are wanting to have their kids memorize the periodic table, you don't have to do that. They don't have to memorize all those numbers, all those atomic masses, all those atomic numbers, all those atomic masses, nor how they bond together. That's not required. So this is a pretty simple standard, actually, which is just showing them a whole bunch of models of things that are very, very simple, like inert atoms, to things that are very, very complex, like diamonds. All right, MS-PS1-1 for teachers. Number 2, how important is content? Well, teachers kind of have a debate on this, on what should we be teaching content or not. And I fall somewhere in the middle. I'm going to tell you the truth. I do believe that content is very, very important. I'm one of those people. I like to teach content. I think students should get content. However, at the same time, they should also obviously be doing something with that content, or else they're just learning a bunch of facts and figures, is what people say. Well, we have a couple of ways that we deal with this. Number 1 is the phenomenon. We talk about that word a lot. If you've heard that word, you might be sick of it. The phenomenon is defined as something that happens that has us ask questions about why that happened. And so that's why we come up with all this science anyway. We look at something, we ask a question about it, and we see if we can help it. So we see if we can find out why that's happening. So, for instance, with gravity, I mean, people saw things fall and knew it fell, but then someone might have asked, well, why does it fall, and how does it fall, and how fast does it fall? Do all things fall the same? And so they do tests to figure this stuff out. So that's what we really want the kids to be doing, is trying to figure things out, showing them some kind of phenomenon and having them figure things out. And with the content, we're just kind of leading them in the right direction. So with this, you might have heard this line a lot. You might have heard a lot storylines. We talk about storylines an awful lot in NGSS. That's kind of become a big word. And let me tell you what a storyline is. Well, honestly, nobody knows. Like, I have looked all over. And I know if you're a teacher watching this and you're like, I know, let me type in right now. I know what a storyline is. I understand that. I've looked on the official NGS website. I've gone to discussion groups. I've gone to professional developments, and everybody kind of gives a different idea of what a storyline is. So what I can gather is, and here seems to be the big takeaway. So before you get on to me or write me and say how you have the right answer and I have the wrong, which I'm sure you do. I have no doubt about that. See if I'm at least going in the right direction. What I take away from a storyline is that it's not it's an actual question. It's just a question that we're leading our way into answering. Some people call them anchoring phenomenon. It guides the instruction. And so in this video, MS-PS1-1, when I present to the kids, what I do is I present it with a question about diamonds. And why are diamonds so hard? What makes them so hard? What about that structure makes them hard? What about their structure makes them to where they can be cut? So that they can be shiny and the light can illuminate out of them. And so I gear the lessons towards that. We're going to learn about how things are structured, how atoms look, how bonding happens, what are extended structures, what are crystals. And when we finally figure out what crystals are and what makes them so hard, then we can get to answering the question in that storyline. So a storyline is just basically a question that's driving your instruction. And hopefully what it is, the storyline drives your instruction over all of this content, and not just one particular day or two days, but everything in your lessons is based on getting to the answer to that question, and that question that hopefully some kind of phenomenon has led you to. The next thing I want to say is that these about content is these were never meant to be taught separately, individually. So like this video right here and the video that I have for the students is on MS-PS1-1, but it's not supposed to be it. Like you're supposed to combine MS-PS1-1 with MS-PS1-2, and you combine those with MS-PS1-4, which talks about states of matter and particle motion and all that stuff. And then you're also with MS-PS1-3, you get the idea. So basically you're looking at a combined unit. So that's another way to address content, is that we don't just hit it and then quit it. We hit it and we keep revisiting it over and over again and showing students how it can be used throughout this wider range. Another way that I suggest teachers that what they do with content, and you can use these videos for that, but you've heard of the flipped classroom. That's something that's very prevalent in science these days. People talk about the flipped classroom. You always know a flipped classroom teacher when you see them because they're very fanatical about the flipped classroom. I flipped my classroom, and you know who you are. It's okay. That's fine. And I think it's a great idea. I haven't quite got there yet, but I understand the concept, and I'm working with it in my way. Let me tell you what a flipped classroom is. A flipped classroom is basically where instead of, like right now, there are thousands of students, well, hundreds of thousands of students in America going home and doing homework, and they're trying to learn, or they're going home and doing homework, and we taught them that content in class, and now they're going home and doing homework on that. But, well, shouldn't the teacher be there when they're doing the homework? Isn't that the most important part? So we have the teacher there when the instructions are being taught, but we don't have the teacher there when the homework is being done. And so what a flipped classroom is it flips those. It has the student learn the content at home, and then when they're doing the work in class, teachers are there to help them. And it's a fantastic concept. And the first question that comes up with that is to say, well, are the kids actually going to learn anything at home? Are they actually going to do this? And the answer is a lot of them will. And for those of them who don't, well, they're not going to do it anyway. So you capitalize on that and let those strong students who understand it, when they're in the classroom and you're working with them, they can start working with the students who aren't getting it or just aren't learning the content at home like they should. So basically, that's what the flipped classroom is. And so these videos help with that. They can watch this content at home, and that's what I do, by the way, in my classroom. Is I teach it in the classroom, but then I have them watch them at home and review them so that we can keep watching it. So I don't just keep teaching the same thing over and over again because they're going to forget it. I teach it once, then I expect them to go home and learn it and relearn it and work with it, and then when they come back, we can work together with it. And it works out. It's a good model because it does help me keep reviewing all those things that we do, and it also, students like it when they can go home and they can see these things. And parents like it especially when they can go home and you can put this on your website, or you can give them a quick YouTube link that they can go to and say, these are the things that we're learning in class. So last thing I wanted to mention was I had a teacher mention this to me about cell phones. Some districts do not allow cell phones, and I'll tell you right now, mine does not allow cell phones, so I can't do this. But they said that videos really help them with cell phones in class because students can use theirs. They can look up this and they can search for whichever part of the video or whatever video they need to help them learn that content or help them on whatever work they're doing in class. So I thought that was a good idea that I wanted to share. So question 3 is, how is this going to be assessed? Now, that's the big question, isn't it? We have these different things that we do in class. How are we really supposed to assess if the students know it? Well, first we have to figure out exactly what the students need to know. And I think that we've done a pretty good job going through that. And now, how are we going to assess that knowledge? And how are they going to do it at the end of the year? A lot of people like these open-ended questions that students can work with, and I think that's fantastic. I think you should be giving these, especially these essential questions, I would just give them as open-ended questions, let the students work their way through them. The tests at the end of the year tend to be more of like a multiple choice. That's a lot easier to grade for states. They normally will have some kind of open-ended question or some kind of scenario. What I do for my students is I developed a multiple choice test. Neon is a chemical element with a symbol Ne and atomic number 10. It is a noble gas, which means because it has a full valence, it does not bond with other atoms. Now notice what I did there. They don't need to know what the chemical symbol is, nor what the atomic number is. And they certainly don't need to know that it has a full valence. So I told them all of that. And even if they don't know what it means, they did pick up on one thing, hopefully, and that is, it does not bond with other atoms. So, which of these best shows a model of the atom neon? Well, an atom that is not bonded with anything else is atom A. This is my most complicated that I like to give the students. It helps them to think it through, especially what models are and how we use them. So this really gets to the heart of the performance expectation, in my opinion. Above is a model of diamond and graphite. Both substances are made of a repeating subunit of only one type of atom, carbon. One can use this evidence to support the claim. So what the students are looking for here is, how can they use those two models? Not what they know or what they think they know or what they think they might have heard, but how specifically can they use those two models to support their claim? So A says carbon can be used to make hundreds of different items, and that's definitely true, but it's not the answer to this question because they can't use that model for that. B says substances made of the same kind of atom can differ if those atoms are bonded together differently, and that's true. And that can be used to support that claim, so B is the correct answer. C says some substances are made of molecules with more than one type of atom called compounds. And that's true, but you can't use that one because that picture because in the picture it only has carbon atoms. And D says some substances are made of subunits that have thousands of atoms, and that's true too, but again, that picture cannot be used for that. So I hope this video has helped you. I do want to show you, I do have that available on my Teacher Pay Teacher website, and you can see right underneath there is a reading selection about atoms, molecules, and extended structures. I want to invite you to go watch my video on MS-PS1-1 for students. Atoms, molecules, and extended structures are making models of atoms and molecules. And have a wonderful day.